Let's suppose that we have the following two objects, plate 1 and plate 2. Now plate 1 has a mass of 10 kilograms, plate 2 has a mass of 15 kilograms. Both plates have a radius of 0.8 meters. Now initially our two plates are separated by some distance and are initially at rest. Now what happens in the beginning is we accelerate plate 1 to angular velocity of 8 radians per second in a time interval of 3 seconds. Knowing that information, we'd like to calculate the angular momentum of plate 1, the torque required to accelerate plate 1, and we also want to calculate the angular velocity of plate 2 after the two plates are connected. So let's begin with part A. We want to calculate the angular momentum of plate 1 after we accelerate plate 1. So recall the formula for angular momentum. Angular momentum, L1, is equal to I1 multiplied by omega 1, where L1 is simply the angular momentum of plate 1, I1 is simply the moment of inertia of plate 1, and omega 1 is simply our angular velocity of plate 1 after it's accelerated to an angular velocity of 8. So our omega 1 is 8 radians per second. Our I1 is simply 1/2 m1 multiplied by r squared. So m1 is 10 kilograms and r is simply 0.8 meters. So we square that, we multiply that by 10 and by 0.5 and multiply that by 8. And we get a quantity of 25.6 kilograms times meters squared divided by seconds is the angular momentum of object 1 of plate 1. Now, what exactly is the net torque acting on plate 1 to accelerate plate 1? Let's suppose the net torque is constant. That means the net torque acting on the object is equal to the change in the angular momentum divided by the change in time. In other words, a certain quantity of torque is required to give the object a certain momentum. And we want to calculate what that torque is. So we simply take change in our angular momentum. Initially, our object was stationary, so our initial L is 0. Our final L is simply this quantity, 25.6 kilograms times meters squared divided by seconds. So we plug that in for the numerator. The denominator is simply our time interval of 3 seconds. So we divide the two numbers and we get approximately 8.5 newtons times meter is our net torque acting on the object. Now, let's move on to the last step. We want to calculate the angular velocity of our two plates after we connect the two plates. Now, note we're going to use the conservation of angular momentum because we're making the assumption that the external net torque acting on the object is 0. If the external net force acting or external net torque acting on the object is 0, we can use the following equation, the following conservation law. The angular momentum before we connect them is equal to the angular momentum after we connect the two plates. So we have the following equation. Before we connect them, we only have plate 1 that is rotating. So I1 multiplied by omega 1 equals, after we connect them, we have to sum up their moment of inertia. So moment of inertia of object 1 plus moment of inertia of object 2 multiplied by whatever the angular velocity of the two objects is. Let's call it simply omega. So now we solve for omega and we get the following result, and let's plug in our values for I. So I1 is simply 1/2 m1 r2 or r squared multiplied by omega 1. I2 is simply 1/2 m1 r squared, and I2 is simply 1/2 m2 r squared. So notice the halves cancel and the r's cancel, and we're left with the following result. m1 multiplied by omega 1 divided by m1 plus m2. So we plug in our value, so 10 multiplied by 8 divided by 10 plus 15 gives us about 3.2 radians per second is the angular velocity of our system of two plates after we connect the two plates. Now once again, we used the conservation of angular momentum because we assume the external torque acting on the object is 0.